just going to lecture a little bit here on chapter 8, where we're at, I believe. So again, yesterday we talked about two sort of important conversions, really one more than the other. But we talked about Avogadro's number. And remember, Avogadro's number is 6.022 times 10 to the 23. And that equals 1 mole of something. And remember that the units sort of associated with Avogadro's number can really change. Most commonly, you will see it as atoms. You'll see it as molecules, but it really can be kind of any unit that you want. And for the most part, Avogadro's number is a conversion factor that we use to go from moles to atoms or molecules, or backwards. So if you need to go in either direction there, Avogadro's number is the one that you want to use to go from moles to atoms or atoms back to molecules. As we also talked about, it's really important maybe not to overuse Avogadro's number, which sometimes this is a problem. People, again, learn the number, kind of want to use it in every situation. Remember, you pretty much need to either be given a number that's in atoms or molecules, or you're asked to solve for something in atoms or molecules. And again, if that is not mentioned, then you really shouldn't use Avogadro's number. The other important thing that we talked about yesterday as well with this, in terms of moles, is again, that is the abbreviation for moles. And again, that is not the abbreviation for molecules. So super common error people make all the time is, like I said yesterday, they kind of see the MOL and they just think molecules instead of moles. So again, that is the definite abbreviation for moles. Probably the conversion factor that we will use more often than not is molar mass. And molar mass does come from the periodic table. And the units of molar mass are grams per mole. And when we calculate the molar mass, the numbers always stays with the grams part and is always per 1 mole of something. And we basically could get that from the periodic table. So if you go to the periodic table, it is going to be the number on the bottom. And as I mentioned yesterday, typically speaking, 4 significant figures is usually what you pull off of the periodic table to use when you're calculating molar mass. And again, it depends on the periodic table if you even got 4 significant figures or not, but the general rule is usually that. And when we do see something like that, that means that there are 12.01 grams of carbon in 1 mole of carbon. Or if you were asked what the molar mass of carbon was, 12.01 grams per mole. And you really can think of molar mass as a conversion factor. And again, you could write it like that with grams on top, moles on the bottom, or you could flip it if you needed to, if you're doing some type of dimensional analysis, moles on top, 12.01 grams on the bottom. And this is a really important, obviously, conversion factor. And that is definitely the one that goes from grams to moles, or you need to go backwards, moles to grams. It is always the molar mass from the periodic table that gets you that. Once again, if it is not just an element and you have some type of compound like water, as we talked about yesterday, you basically just add up all the parts to it. So there would be 2 hydrogens at 1.008 grams per mole, plus our 1 oxygen from the periodic table of 16. And that would give you a molar mass of 18.02 grams per mole, will be the molar mass there of water. Now, a really important thing to keep in mind is, again, if you have, say, water or something in a future problem where it's in an equation and it's got like a number in front of it, that will have no effect on the molar mass. So if you're asked to calculate the molar mass for water, it should be this number here, the 18.02. You will always calculate molar mass based on just the formula by itself, not any type of coefficient that you will find like in a balanced equation. And that also later on when we do things like stoichiometry, that's a super common error as well. People go calculate the molar mass. They use the coefficients in the balanced equation. You don't want to do that. So if you happen to come across something in an equation and it has a coefficient, and you need the molar mass, all you have to do is just take the formula by itself and just do it for one of the formulas. And that's really what molar mass is. It's how many grams there are in basically 1 mole of that thing. And 1 mole would be just one formula sort of unit, if you will. Any questions on any of that stuff there from last time? We also, speaking of formulas, talked about the idea that from an actual formula, you could get some conversion factors. And those numbers on the bottom, as we will talk about here in a second, they are the moles of each of those things. And in an example we did at the very end, if you were not interested maybe in the whole thing, but maybe just the hydrogen part of it or the oxygen part of it, you could actually use the formula itself as sort of a conversion factor, mole to mole conversion factor to go from the whole thing to one of those sort of elements by itself. All right, so the next thing we're going to talk about are different types of formulas. And the first type of formula is a molecular formula. And a molecular formula really is a formula that really tells you exactly what is present. So when you have a molecular formula, it pretty much will tell you what is present. And we know a molecule needs to be at least 2 or more atoms. They could be the same element or different elements, but you need at least 2 or more atoms to make a molecule. Now, a chemical formula expresses exactly what is there. And sometimes formulas are more expressive than others. So, for example, you could have a formula, once again, that is CH3 COOH, or you could have one that is C2H4O2. These are actually the same thing. One just gives you a little bit more information about how it's sort of connected. And the one on the left is that. The one on the left here gives us a little bit more information about really how it's sort of bonded together. That's acetic acid. And if you drew acetic acid, it again would look something like this, a little ethanoic acid, acetic acid. And you can see in the first formula here on the left, it really does give you sort of how it's put together. You have a CH3, that's a carbon and 3 hydrogens attached to each other. You have this sort of COOH, which if you continue to take organic, you'll learn is the carboxylic acid group there. And again, it gives you a little bit more information about how it's sort of connected. The other formula basically just tells you, hey, there's 2 carbons, there's 4 hydrogens, and 2 oxygens. It really doesn't give you sort of structural information about how it's sort of put together. And again, that's a very common thing. Sometimes you'll just get kind of just the bare bones of these are the elements that are there. And sometimes you'll get a little bit more sort of structural information in a formula. Any questions on that there? So the molecular formula, again, is the one that tells you exactly what is present. The simplest molecular formulas we could have is really diatomic molecules, since there's only 2. So obviously O2, right, H2, these are all molecular formulas. In their simplest forms, like I said, again, it can give you basically what's present, or it can give you some information. So this is the same idea here. Both of these formulas are the exact same thing. If you add up the carbons and the hydrogens in each, you will end up with the same amount. But once again, the second one in this case gives you a little bit more information about how it's put together. And ethanol looks something like this, or ethyl alcohol. Looks a little bit like this. And once again, you see a CH3, which is a CH3, a CH2, a carbon and 2 hydrogens, and an OH and an OH. So again, it gives you sort of how it's put together. The other one, again, just basically gives you, hey, there's 2 carbons, 6 hydrogens, and 1 oxygen in this particular compound. I would say in a lot of cases, you do see a lot of times people will kind of write the molecular formula a lot of times to indicate some of the structural components of it, how it's put together. That's a very common way that people kind of write formulas. Now, another type of formula that's an important formula is an empirical formula. And an empirical formula, unlike a molecular formula necessarily, in an empirical formula, that is the simplest kind of whole number ratio of what's present. So it may not always be exactly what's there, but it's like this simplest sort of ratio of what is present in that particular compound. So for example, here with hydrogen peroxide, H2O2 is the molecular formula. And when we look at the relationship in the molecular formula, there are basically two hydrogens for every two oxygens. And that's the same as a one-to-one relationship. And again, it could reduce down to HO, which is the empirical formula in this case. And the empirical formula is the simplest whole number ratio of what's present. You cannot have like a half of, atom or something like that, or mole or something. So you do need to have whole numbers on the bottom here. So you can't have, partial of each of these elements present. Again, if you had C6H6, that is again 6 carbons for every 6 hydrogens. That is also a one-to-one relationship. And that would reduce down to CH in this case as the empirical formula. So the empirical formula is the simplest whole number ratio of what is present. Now, sometimes as we will see, the empirical formula and the molecular formula are the same. And water, for example, in water, we have 2 hydrogens for every 1 oxygen. There's no way to reduce that down anymore and still have whole numbers. So that's as far as you could go. So something like water is both the molecular formula and the empirical formula. Now, one place where we typically do see the empirical formula always is with ionic compounds. So if you think about what we talked about with naming, when we take something that is positive and something that is negative, we put it together in the simplest way possible to get 0 charge. And that's basically an empirical formula. So all ionic compounds, when you look at their formulas, they're basically empirical formulas. They're the simplest way possible to do that. Again, you could, for example, with calcium and bromine or bromide, obviously the simplest way possible to put those together to get no charge is 2 of each. You could have, if you wanted to, and that would give you a 1-to-2 ratio of calcium to bromine. You could have done like a 2-to-4 ratio. I would still give you 0, but that is not the simplest possible way of putting that together. And you would reduce it down to calcium and 2 bromines. And that is a simple formula. So all ionic formulas are empirical formulas. Now, what are empirical formulas? Well, empirical formulas are really very simple formulas that you can very easily sort of figure out in the laboratory. You could do a very simple experiment and you could come up with the empirical formula of a particular compound, which I think we might do a little bit later on in a couple of weeks, maybe. And it's a very simple process by just, for example, looking at the difference in masses, and you can calculate the empirical formula very simply by knowing the difference in masses that occur. So for example, if you did a reaction like we would do, magnesium and some oxygen to make magnesium oxide, you can know the mass of the magnesium to start with. You can figure out how much oxygen gets put on there. And now you know the mass of each element. And you can do a calculation the way we'll talk about to basically figure out the empirical formula. Now we take a look here at hydrazine N2H4. That again is a 2-to-4 ratio of nitrogens to hydrogens. If you divide everybody here by 2, that reduces down to a 1 nitrogen to 2 hydrogen ratio here. And the empirical formula would be NH2. So it is only the molecular formula that tells you the actual numbers of atoms present. The empirical formula, once again, is just the simplest whole number representation of the elements that are present. As I mentioned a second ago, a lot of molecules, the empirical formula and the molecular formula will be the same. Again, like we just talked about with water, there's no way to reduce that down any further and still get a whole number. Same thing with ammonia or carbon dioxide. Again, no way to go any further down, reducing, and still end up with a whole number. All right, so take a moment for each of these and figure out the empirical formulas for each. Okay, so let's take a look. So again, these are the molecular formulas. So we start here at the first one. We basically have 2 carbons for every 2 hydrogens. Again, we can reduce this down and still get whole numbers. Can basically divide everybody by 2. Gives us basically a 1 carbon to 1 hydrogen relationship. And that would give us our empirical formula here again, which would be CH. If we come over here to diiodine pentoxide, that is 2 iodines for every 5 oxygens. That is, again, as far as you could go. There's no way to reduce that down and still get a whole number. So here, our molecular formula and our empirical formula would be the same. It's basically as simple as you can get. And then obviously here for glucose, those 6 carbons for 12 hydrogens for 6 oxygens. Again, we could divide everybody here by 6 and still hit whole numbers. Gives us a 1 carbon to 2 hydrogens to 1 oxygen in this case. And that would give us our empirical formula here of CH2O in this case. Any questions on that there? All right, so another important sort of aspect of really empirical formula and molecular formula calculations is what is known as percent composition by mass. And basically, percent composition by mass is if you know the molar mass of a compound and you know the formula, you can figure out the percent of carbon that's present in that compound, for example, percent of oxygen, percent of hydrogen is there. So you basically take the mass of each element and divide it by the molar mass of the compound and then actually multiply by 100. So let's take a look here. If we have H2O2 and we wanted to figure out the percent composition here of each of the elements involved, the first thing that we would want to do is calculate the molar mass of this compound. So once again, if we go to the periodic table, we will see a couple of numbers there. For hydrogen, 1.008, and for oxygen, we will see 16. So in this particular case, the molar mass here of our compound would be by adding the parts up. So 2 hydrogens at 1.008 grams per mole takes care of the hydrogen part, plus 2 oxygens at 16 grams per mole takes care of the oxygen part. And that's going to give us a molar mass in this case of, looks like 3402, we'll call it. Now, if we wanted the percentage of hydrogen in this compound, we would take the mass of hydrogen, which would actually just be this part. So we'll take 2 times 1.008. And we would divide it by the molar mass of the entire compound, which is 3402. And times it by 100%. And that's going to get us here divided by 3402 times 100. We can see that in this particular case, 5.926% of it by mass is made up of hydrogen. We could do the exact same calculation for oxygen in this case. In this case, we do have 2 oxygens, and it basically will be this. So 2 times 16, which is 32, divided by the molar mass of the entire compound, and times 100%. And that will get us here 32 divided by 3402 times 100. About 94.06% is made up of oxygen in this case. Obviously, these are the 2 elements involved. And we can see by mass is mainly made up of oxygen by mass. We also could see that we got approximately there 100% total. By the way, because these are the 2 only elements in this compound, once you actually calculated this guy, alternatively, you could just go 100% minus the percent of hydrogen, and that would get you there. Again, with rounding, it might be slightly different, but in the ballpark, you could get it as well since that's the only one sort of left. Any questions on that there? Now, as we saw earlier, this is the molecular formula of hydrogen peroxide. And if we look at the empirical formula for hydrogen peroxide, which is HO, what do we end up with in terms of our percentages? So if we take a look at this, we would now want the molar mass here of HO, and that's going to be 1.008 for our hydrogen, plus 16 for our oxygen. And that's going to get us a 17.008. And at this point, we could do our percentage of hydrogen, and that is 1.008 grams per mole, as there's only one, divided by 17. I'll call it 01. I'll just round a little bit there, times 100%. And that's going to get us 1.008 divided by 17.01 times 100%, gets us a 5.926% hydrogen. And if we do oxygen, it will come out very similar, 16 grams per mole for their one oxygen, divided by 1701 grams per mole times 100%. And we will end up with about 94.06% oxygen. And if we compare our empirical formulas sort of percentages to our molecular formulas percentages, they are basically the exact same percentages. And that's because, again, the empirical formula is based off the molecular formula. It is the simplest whole number ratio. So you will still have really the same sort of ratio of hydrogen to oxygen in this particular example. And that will give you basically the same percentage by mass of each of those elements. So if you did the percent composition by mass of the molecular formula or the empirical formula, you will end up with the same percentages for each element involved. Questions on that? By the way, obviously, it should add up to about 100% when you're done. Yeah. And again, with rounding, maybe a little higher or a little lower, but it should definitely be in the 100% ballpark if you have all the stuff there. So why don't you give it a go here? Calculate percent composition of each element. Phosphoric acid, so hydrogen 1.008. The 97 for phosphorus, and oxygen 16. All right, so take a few. And here, basically, we have just the formula. So we want the percent composition of hydrogen, phosphorus, and oxygen here. So we're going to start with the molar mass of H3PO4. There are 3 hydrogens at 1.008 each. Again, for the hydrogen, we're going to add it to our 1 phosphorus at 3097. And then we're going to add it to 4 times our oxygen's molar mass from the periodic table. And that's going to give us 162, I think, grams per mole. Now we can look at each of the sort of elements individually. And for our percent hydrogen, we're going to take our 3 times our 1.008. That'll give us the mass of the 3 hydrogens that are present, divided by the molar mass of the compound times 100%. And that's going to get us here something. Get us 3 times 1.008. That's 31. Try that again. 3 times 1.008 divided by 162 times 100. I guess it's about 1.867% hydrogen. We will then do the same thing for our other ones present. So we could then do phosphorus next. And I got the double check my molar mass. I feel like it's like wrong here. 1.608 plus 3097 plus 4 times 16. Yeah, that's like way off. 97, 99 has that. That seems much better. Like a 98, 97, 99. Jeez. That's what happens when you try to go by memory. That's not a good thing. All right, let's try that again. All right, so we'll just cut it out of the video. Nobody will see it. All right, 97.99 grams per mole. Sound better? All right, let's do that over here. All right, so 3 times 1.008 divided by 97.99 times 100. How about 3.086% hydrogen? We'll do our percent phosphorus, which is 3097 grams per mole over 97.99 times 100%. And that's going to get us here about 31.61% phosphorus. And lastly, our percent oxygen, 4 times 16 divided by 97.99 times 100%. So 4 times 16 divided by 97.99 going to get us a 65.31% oxygen. So hopefully I did better this time with my calculator than I did last time. There we go. And if we add it up, we're about 100%, which is good. We also, obviously, at this point, could have added those together and subtracted 100 and get the last element as well the same way. Any questions on percent composition there? And it helps with the right number. It's probably a little bit easier. Now, percent composition by mass is used a lot to calculate empirical formulas. And what we're going to talk about now are the steps that you will follow to actually calculate an empirical formula. So if you don't have the molecular formula given to you like in the previous problems, and you're asked to calculate the empirical formula, there's several steps that you follow. And the steps to sort of calculate an empirical formula are as follows. I would say that in a lot of problems, you will be given, a lot of times, the percent composition by mass, like we just did. And very commonly in empirical formula problems, you're told, hey, there's like 25% carbon and 7% hydrogen and so forth. Now, obviously, as you're probably aware of, one of the easiest ways to kind of turn a percentage into a usable number is to assume you have 100 of something, right? So it basically keeps the number the same. So if you are given the percent composition by mass, you basically want to turn them into grams. And one way you could do that is assume you have 100 grams of something. It would just keep the numbers the same. But really, the first step is whatever information they give you, you basically need to get to grams of each element. And I will say, like I said, percent composition by mass is the most common way that you kind of see in empirical formula problems. Once you have grams of each element that's present, the next thing that you want to do is convert your grams to moles. And we know how to do that from what we've been talking about. That is going to be using the molar mass from the periodic table to do that. So at this point, whatever they give you, the information, you want to get them to grams. Once you have them in grams, you want to use the periodic table, and you now want to convert each element into moles. Once you have each element into moles, you are then going to divide by the smallest number of moles. So for example, let's just say you did step number 2 and you ended up with 2 moles of A and you ended up with 4 moles of B. And again, these are sort of the moles that you ended up with when you did step number 2. Now, in this case, what we would do is we would look at each of those moles and we would see that 2 moles is the smallest number of moles. So we would divide this guy by 2 moles, which is the smallest. We would divide this guy by 2 moles, which is the smallest. And we will end up with a 1, obviously, for A, and we would end up with a 2 for B. And if you do this and you end up with whole numbers, that is going to be your empirical formula. So your empirical formula in this made-up example would be A1 and B2 would give you your empirical formula. Now, if you get a whole number or really, really close to a whole number, like maybe 1.99 or something like that, 1.98, maybe just a little bit over a whole number, 2.01 and stuff like that, 2.03, those are close enough to sort of round to a whole number. And let's just say, though, that you did step number 2 and you ended up with a different arrangement of moles. Let's say you did step number 2 and you ended up with 2 moles of A, but you ended up with 5 moles of B. Now, in this particular case, you would still divide by the smallest, which is 2. So we would divide this guy by 2 moles, and we divide this guy by 2 moles. That's going to give us a 1 for A, and it's going to give us a 2.5 for our B. And that would give us an empirical formula of A, B 2.5. This is a problem because you cannot have like a half a B there, right? So I left it somewhere, I kind of lost it. So remember that basically those numbers on the bottom need to be whole numbers. And this is not a whole number. This, by the way, at 2.5 is too far to round. So when you're calculating empirical formulas, there are certain numbers that you get are considered too far to round. 0.5 is definitely too far to round to the whole number. And also a very common ending is like 0.33 is another very common ending. And that also is kind of like too far to round. So when you're calculating empirical formulas, if it's not almost on that whole number, it's probably too far to round. Yeah, so you usually got to be very, very close to a whole number to round. So what do we do in this case? What we have to do in this case is figure out a number that we can multiply that empirical formula by and end up with a whole number. So very simply, all you have to do is just like 2.5 times 1 is 2.5. 2.5 times 2 is 5. So that is a whole number. And that's going to work. So what I need to do is take this 2, which is the factor, and I need to multiply it by both of those guys, not just the one that's a decimal. So I need to multiply the A by 2, and that will give me A2. The B by 2 will give me B5. And this will now give me whole numbers, and this will give me my proper empirical formula. So like I said, if you end up with like when you're dividing like a 0.33 is very common, 0.5 is very common. Again, these are usually too far to round. You need to kind of come up with a number to multiply everybody by that will put everybody into a whole number. Any questions on that there? So let's take a look at one here together to finish up on and see how we do this. So we have ascorbic acid, which is vitamin C, is composed of 40.92% carbon, 4.58% hydrogen, and 54.5% oxygen. So the first thing you want to do is, since we're given basically the percentages of each of these, we got 40.92% carbon. We got 4.58% hydrogen, and we got 54.50% oxygen. One of the things you usually want to kind of check is to make sure that all these percentages add up to pretty close to 100%, which it does in this case. You got about 54, and 40 is 94 and a half, and you got 4.5. So you basically got 100%. Again, if you get to this part and you add up the percentages and it doesn't add up to 100%, you're probably missing something, right? There's some type of element you're missing. And you could usually figure out the missing percentage by subtracting from 100. So add up the other percentages and then subtract from 100, and I'll give you like the missing one. And that sometimes is a problem in empirical formulas. They'll give you like maybe the percentages of two of the three things and not the third thing. So again, you can add them together and subtract by 100. Since we could do, we do have 100%, we could assume that we have 100 grams. And again, the purpose of this is just to keep the numbers the same. So that would turn my 40.92% into 40.92 grams of carbon. It would turn my 4.58% into 4.58 grams of hydrogen, and my 54.50% into grams of oxygen. Now that we have these guys converted into grams, so we got everybody into grams, now we need to convert everybody into moles. And again, we're going to use the molar mass to do that. So we got them to grams. Now using the molar mass from the periodic table for carbon, it is 12.01 grams per mole. For hydrogen, it is 1.008 grams, 8 grams per mole. And for oxygen, it is 16. Again, dimensional analysis, opposites cancel. And that's going to now give us basically the moles of each of these things. So we'll go 40.92 divided by 12.01. We got 3.407 moles of carbon. 4.58 divided by 1.008. 4.544 moles of hydrogen. And lastly, 54.5 divided by 16, 3.406 moles of oxygen. At this point, once we have it into moles of each element, we're then going to divide by the smallest. And in this case, they're pretty much both the same, but I guess technically speaking, this guy on the bottom here is slightly smaller, 3.406 moles. We're going to divide this guy by 3.406 moles, and we'll divide this guy by 3.406 moles. That's going to give us a 1 for our carbon, 4.544 divided by 3.406 is going to give us a 1.33, and we will end up with a 1. First off, any questions so far? So percentages into grams, grams into moles, divide by the smallest. This technically would give us, I'm just going to borrow some room up here up on top, an empirical formula at this point of C1 H 1.33 and our oxygen of 1. As I mentioned a second ago, this is obviously not a whole number, and that ending of 0.33, which is very common as well, is too far to round. So here we need to find a number that we can multiply the 1.33 by that will give us pretty close to a whole number. So again, if you just trial by error, 1.33 times 1 is 1.33. 1.33 times 2 is 2.66. 1.33 times 3 is 3.99. 3.99 is close enough to a whole number to basically be 4. Yeah. So that is the factor by which we want to multiply, once again here, not just the 1.33 guy by, but we want to multiply everybody by that factor of 3. And if I do so, I'll end up with C3, H4, and O3. And now we have all whole numbers, and we have our empirical formula at this point. Any questions on those steps there? So basically get it to grams, grams to moles, smallest. If you hit all whole numbers, you're good. If not, got to find a factor to multiply. And again, you don't always have to find a factor. A lot of times you will hit pretty much whole numbers, and you'll be in good shape. Any questions on how to calculate the empirical formula? All right. Place I